All right, so here's the hands-on version where you just do all these things in Google Colab. And I think I'm not going to do it live, but just talk about it. So you import some stuff in a block of Google Colab, then you download the data. This is included in the libraries. Here's coming from GitHub. So you get this California housing price data from the 90s. And HEAD shows you what kind of data you're dealing with. So you got rooms, bedrooms, median house value, ocean proximity, and we're trying to predict this thing, median house value, from all the other quantities. So you can do a value counts in your Python to see what values are here. There's 5 possible values, and as you can see, wildly varying numbers of housing districts in those categories. And you can do describe to get a statistical description of each of these things. That may help. And then you can make the histograms, and the histograms are really quite helpful. And you can see a few things, like, for example, if I plot, I think this is the price, or this histogram. This is how many instances there are in categories of rooms. And you can see that it's not a Gaussian distribution at all. There are apparently, because this is against longitude. In California, there's places near San Francisco and places near Los Angeles and not much else. So it's not a Gaussian distribution by longitude. It's basically 2 Gaussians put together. And then same thing with latitude. And here's housing median age, which has a very strange distribution, as we've said before. Maybe there was a boom of housing at this time and at this time, or maybe it's some kind of defect in the data. This is certainly a defect in the data. Apparently, they wouldn't let anything be older than 50 years, so this is really 50 or greater and should not be mathematically interpreted as exactly 50. Then here's rooms and bedrooms and house value. Those all look reasonably Poisson distributed, which is close to Gaussian if you just change this into another scale, like I think a logarithm or something. And the same thing of these parameters down here, rooms, bedrooms, and households. This gives you a clue. And here's another one of these flaws. The median house value hits a maximum value, and too many instances are at that number, more than can really be true. It must be including some above it. So you're probably going to have to remove these from the data set if you want to get an accurate representation of the real housing price. So here's a randomly created test set where it just shuffled and split, taking random 20% and putting them out. And then if you do that, your training set will have these properties, this many in the various categories. And if you do it again, you'll get different values. It's randomly choosing 20% to be the test data every time, which would be okay if you don't know anything more about them, if they're all completely equal. But in this case, we know it's a problem. As you said, if you had something dependent on female to male, you wouldn't want to allow randomness to give you a strange percentage of females in your test set. So you do stratified sampling. And so what we do is we want to make sure we know median income is very important to predict house prices. It's the most important thing. So we want to make sure we haven't randomly chosen an unrepresentative sample of median incomes. So you break it into categories, 5 buckets, and then you choose the exact right number of each bucket. So you split the data using stratified sampling, and now in your training set, you have 35%, 31%, 17%, and in your test set, you have 35%, 31%, 17%. You have exactly the right number in each of these, so you have tried to remove the largest source of bias in your test set. And if you created your test set randomly, then it would be quite a bit different, like 11.5, 11.0, 31, 32. That's the random sample, which is not as good in that regard. All right, so after you've done that, you can visualize the data, plotting them by location, using transparent dots to make it easier to see, to some extent, the huge concentration of houses near the San Francisco or Los Angeles area, although even the transparent dots is still not giving you a very good representation. You can include population and price. Here's median house value, here's population. Yeah, the size of the dots is population, the color of the dots is house value, and the location is latitude and longitude. So you got all 4 of those parameters on one graph. And now you can do the correlations we talked about before. This is what shows you how predictive various things are. To predict this, the most valuable thing is median income, but these other things like rooms have some predictive power. And you can make scatter plots across the various parameters to see it. This is a strong correlation. And this is just another view of the same correlation. And so here you see the rows of data that are not really accurately being measured. Too many houses in this zone are placed at these specific values when that doesn't appear correct. And now we can try the attribute combinations where you combine two parameters by dividing one by another to make a new parameter. And now you'll see that rooms per house, which is one of these you calculated, rooms per house is far more useful, 14% correlation, than any other things. And bedrooms ratio is really predictive, 25% correlation, which is worth far more than bedrooms by themselves and total rooms by themselves. So it's often quite valuable to create synthetic new parameters out of the existing ones that turn out to be more useful to predict the value. And there's more going on in the book, but that's as far as I went in this hands-on project. And this is it. You spend a lot of your time massaging data to get it ready to go in machine learning. All right.